In this video, we will examine a few questions from our worksheet on projectile motion. Alright? Now, it previously would have derived certain equations which relate to a certain type of projectile motion, that is where the body was projected from a certain level and landed back at that initial level of projection. And throughout this exercise, we may use some of these equations, but these equations will not necessarily apply to every situation. But for the sake of the situations where they do apply, we will use them. And the equations, for instance, are the maximum height reach. Let's call that H max. This is equal to V sine theta all squared over 2g. The time taken to reach maximum height, let's call that T max. H will be equal to V sine theta over g. The time of flight, horizontal time of flight, will be equal to 2 V sine theta over g. The horizontal range, R, is equal to V squared sine 2 theta over g. And the equation of the path is given as y equals x tan theta minus g x squared 1 plus tan squared theta all over v squared. Right? So those are the equations that we would have derived pertaining to projectile motion, and throughout this video we might use some of these equations. Right? Good. Now, having said that, let's begin by looking at question 1. So question 1 says a particle is projected with a speed of 25 meters per second at 30 degrees above the horizontal. Find A, the time taken to reach the greatest point of its trajectory, and B, the magnitude and direction of its velocity after 2 seconds. So let's try to represent the situation, right? So we have a body which is projected at a speed of 30 degrees above the horizontal. So let this be a horizontal. So it's projected above the horizontal. Now we don't know if the object is going to return and its initial level of projection, but let's just say for argument's sake it does, right? So let's just let that be the possible path of the object, right? The possible trajectory. So the velocity will be at an angle of 30 degrees to the horizontal. So this is the initial velocity, which is 25 meters per second. Right? So that was what we're given. Right? And of course, throughout this case, we'll do the motion like this, or acceleration A, of course, will be equal to minus g, and that, of course, would have been used to derive these equations. Right? So we want to find the time taken to reach the greatest point of its trajectory. Now, when we speak about the greatest point of its trajectory, we're talking about the maximum height. So in other words, then we want to find the time taken to reach a maximum height, and of course, you can use a formula for that. So the time taken to reach maximum height is equal to V sine theta over g. Right? So in this case, we have the initial velocity of projection 25 meters per second. So we'll say that V equals 25 meters per second, and the angle theta is equal to 30 degrees. So therefore, the time taken to reach maximum height, T max, is equal to V sine theta over g. And this gives us 25 sine 30 divided by 10. Now, sine of 30, that is a half. Half of 25, that is 12.5 divided by 10. And so this gives us the time taken to reach maximum height is equal to 1.25 seconds. Alright? So 1.25 seconds. Good. Now, the next part of the question wants us to find the time taken, or the magnitude and direction of its velocity after 2 seconds. Now, let's analyze the situation. Now, basically, it takes a time of 1.25 seconds to reach a maximum height. So that means that after 1.25 seconds, the body will only be traveling horizontally, as the vertical component of its velocity will be 0, right? And this, of course, will be v cos theta. So after 1.25 seconds, it will only be moving horizontally as it is at its maximum height, and the vertical velocity, Vy, will be equal to 0. Now, because of the nature of this motion, if it was to return to its initial level of projection, right? So let's say this point is O, and this point is A, which is at its initial level of projection, then the time of flight, or the time taken to return, would be twice the time taken to reach maximum height, and that would have been 2.5 seconds. So what is the importance of that? Because you know it would have taken 2.5 seconds to return to its initial level of projection, it therefore means that after 2 seconds, the object is shy of that point, and so it will have both a horizontal velocity and a vertical velocity, right? Or a vertical component and a horizontal component of its velocity. Good? And therefore, what we want to find is the magnitude and direction of its velocity after 2 seconds. And therefore, its resultant velocity will always be tangential to the actual path, right? So trying to represent the situation here. So what we want to find is the horizontal component of its velocity, the vertical component of its velocity, and that will therefore allow us to find the velocity v at a certain time. So let this angle, of course, be theta, right? And this, if we complete our vector triangle, then this basically represents the completed triangle, and this will be our vertical component vy, this is a horizontal component vx, and our velocity v, right? This is our velocity v. So let's examine horizontal direction. Now horizontally, we know that there is no resultant force acting on the body, and we ignore the effects of wind resistance, so we know that the velocity in the horizontal direction will be constant and will always equal the horizontal component of its initial launch velocity. So we know that at any given point, Vx, so the horizontal velocity or the velocity in the x direction, is given by v cos theta, right? Which is basically the initial horizontal component of this launch velocity, and so this gives us 25 cos 30, which is 25 times 0.866, and that gives us so 25 times 0.866, and that gives us 21.7 meters per second, right? So the horizontal component of the velocity is 21.7 meters per second. Now let's proceed to finding the vertical component of the velocity after 2 seconds. So even though we're looking at projectile motion, of course, in some cases our regular equations of motion still apply, but of course Alright, so let's now examine the vertical direction. So vertically, right, we have the initial vertical velocity, u is equal to v sine theta, which of course was equal to 25 sine 30. And of course sine of 30 degrees is equal to a half. So half of this will give us 12.5 meters per second, right? So we know that basically A is equal to minus G, and for simplicity we're using G as 10, so this is equal to minus 10 meters per second squared. We're given the time t equals 2.0 seconds, and we want to find the vertical component of velocity Vy, right? So therefore, we're going to use the equation v equals u plus at, or we can say that vy is equal to u plus at, right? So since we already expressed u in terms of the components of the initial launch velocity, we can just use the equation v equals u plus at, and what we get is that is equal to 12.5 plus minus 10 times 2, and so this gives us 12.5 minus 20, which gives us minus 7.5 meters per second. So after 2 seconds, its vertical velocity is equal to minus 7.5 meters per second. Now, why is it negative? So the horizontal velocity, Vx, equals 21.7, and this will be equal to minus 7.5, So just leaving off the units. Now remember that velocity is a vector quantity. So if while it is going up in one direction, it's treated as being positive, then in the opposite direction, it must be treated as being negative. And with this projectile motion, we generally use the sign convention that up is positive. So while it is traveling up, the velocity will be treated as being positive, but while it is on its way down, the velocity will be negative. And therefore, this is the significance of a negative velocity. Then this tells us that the object is actually on its way back down, right? So what we want to find is the velocity v. And so because what we have here is a x component meeting a y component, then this basically forms a right angle triangle, and we can use Pythagoras' theorem to say that v squared is equal to vx squared plus vy squared. And so we get that v squared is equal to 21.7 squared plus minus 7.5 squared. And that gives us, so let's work that out. So 21.7 squared plus 7.5 squared. And v squared is equal to approximately 527. This would be meters squared per second squared. And therefore v is equal to the root of 527. Right? So second function square root, second function answer. And this gives us approximately 22.9, or we could round to 23. So approximately 23 meters per second. Right? But let's leave it at 22.9. So approximately 22.9 meters per second, right? So that is the magnitude of the velocity, right? So the magnitude is 22.9 meters per second, right? So, however, if we're talking about the direction, because it is now moving downwards, then of course we'll treat it as a negative velocity. But we know it is actually moving downwards, so we'll just leave it as 22.9. Now we need to find the direction. So we have the angle theta, which we want to find, and the velocity v is acting below the horizontal, theta degrees below the horizontal. So tan theta equals opposite over adjacent, and so we see that tan theta is equal to 7.5 over 21.7, and therefore theta is equal to the tan inverse of that. So tan inverse of 7.5 over 21.7, and that should give us 19.1 degrees. So approximately 19.1 degrees. So this would be 19.1 degrees below the horizontal. Right? So therefore, after 2 seconds, the magnitude of its velocity is 22.9 meters per second at an angle of 19.1 degrees below the horizontal. All right, so that was question 1 from our worksheet. We'll next look at question 2 from the worksheet. So question 2 says, an arrow which has an initial speed of 40 meters per second is aimed at a target which is level with it at a distance of 100 meters from the point of projection. Find the least time of flight for the arrow to hit the target. Now, usually we express these situations on a diagram, and from there we try to analyze the situation, right? So we're told that an arrow, we're given its initial speed, it's aimed at a target which is level with it at a distance of 100 meters. So what is the significance of this? Let's try to represent the path of the arrow. So the arrow is fired, and it basically travels along this path. So let's say the arrow is fired from O and it lands at A. It's going to be launched with a velocity of 40 meters per second, right? Now what we're told is that when the target is at the same level as the arrow. So this means that the arrow returns its initial level of projection, and we're given how far the target is from the arrow. So we're given that the distance is 100 meters. So the distance OA represents 100 meters. And therefore, what this means is that because O and A are at the same initial level of projection, then this distance represents our horizontal range R, which is equal to 100 meters. Right? So we don't know the angle of projection. Let's call it theta. But we do know the speed with which the body was projected. Right? So what they want us to find is the least time of flight for the arrow to hit the target. So let's look at the information that we have. We have the horizontal range R, we have the launch velocity, and that basically is the only information that we have. So if you look at the list of equations that we have a formula for the horizontal range, and if you look at this formula carefully, we know R, we know V, we know G, so we can therefore use this formula to find the possible values of the angle theta, and then with those possible values of angle theta, we could find the corresponding times of flight, right? So we're going to say that R is equal to V squared sine 2 theta over G. So if we substitute the values, we get that 100 is equal to 40 squared times sine 2 theta over 10. So we simplify this, we get 100 is equal to 40 squared, that's 1600 divided by 10, this is 160 sine 2 theta. So this is 160, right? So therefore what we have is sine 2 theta is equal to 100 over 160. So sine 2 theta, the zeros cancels, 2 into 10, 5, 2 into 6, that's 8. 8 into 5, that's approximately 8 into 5, that's 0.625. So sine 2 theta is equal to 0.625. Good? Then we say that 2 theta is equal to the sine inverse of 0.625. And we go to our calculator, right? Let me just check my math there to see that is correct. So 10 divided by 16, right, 0.625. So 40 squared, that is 1600 divided by 10, 160. Right, so 0.625. So sine inverse of 0.625 equals. So this gives us 38.9 degrees. 2 theta equals 38.9 degrees. But is that the only possible value for that angle 2 theta? No. If you remember from a look at trigonometry, then we should know basically that, well, A, S, T, C. So all school teachers cuss, or all school teachers care. That is a little mnemonic which is used to remember that. Of course, neither version is true. So what this is basically saying, in the first quadrant, all trig ratios are positive. In the second quadrant, sine is positive, and so on. So since you're looking at sine of an angle and the value is actually positive, we'll get a value in the first quadrant, but in the second quadrant there is also a value, and to get that value we subtract 38.9 from 180 degrees, and this gives us that would almost be 140, so if it was 39, 141, 141.1. So 141.1, if I'm not mistaken. So 180 minus 38.9. Right, 141.1. So these are the two values for twice the angle theta. So 2 theta equals that, which means that theta is equal to a half of that, which is going to be approximately 19.5 degrees, or we divide it by 2, and that gives us about 70.55, 70.6. 70.6 degrees, right? So those are the two possible values of the launch angle theta, right? Now the question did not ask us for the possible values of the launch angle. It asked for the minimum time of flight. So what we will therefore do is to basically use these two angles to calculate the corresponding time of flights and see which of them is smaller. So the time of flight is given by the equation TF is equal to 2 V sine theta over G. But of course, from our knowledge of sine of angles, we should be able to tell that the smaller the angle, then the smaller the sine of the angle. So naturally, the larger value of the time of flight will occur when the angle is equal to 70.6 degrees. So therefore, the minimum time of flight, which is what the question asks for, is it? Right, the least time of flight occurs when theta equals 19.5. So therefore, TF, this will be equal to 2 times 40 times sine of 19.5 degrees all over 10, and this should give us 2.6 seconds. All right, so the minimum time of flight occurs when the launch angle is the smaller of the two, 19.5 degrees, and this basically gives us 2.6 seconds. All right, so just check to verify. So sine 19.5 equals times 80, or sine 19.5 times 80 divided by 10. Right, so 2.6, 2.7. Right, so about 2.7 seconds. So 2.67 to one decimal place is 2.7 seconds. Right? So therefore, this would represent the least of the two times of flight. Now, if we were to represent the situation, how would this differ on a diagram like this? So a smaller angle will basically have a flatter trajectory, right? So if this say angle represents a 19.5, the 70.6 will obviously achieve the same range, but this would mean that the object will rise to a much larger maximum height before returning to the initial level of projection, right? So this flatter trajectory is normally typical of a smaller launch angle, and the steeper one typical of a larger launch angle. All right, so that was question 2 from our worksheet. All right, so let's look at number 3. Number 3 says a pebble is thrown from the top of a cliff at a speed of 10 meters per second and at 30 degrees above the horizontal. If it hits the sea below the cliff 6 seconds later, find A, the height of the cliff, and B, the distance from the base of the cliff at which a pebble falls into the sea. So once again, we'll represent our situation using a simple diagram. So let this be our cliff, right? This is our cliff, and this is the sea, right? So the pebble is going to be projected like this, along a path like this, right? And it then lands into the sea. Good? So this launch angle, we're told, which makes the horizontal, this angle is 30 degrees, right? So 30 degrees. And the launch velocity is 10 meters per second. Right? So the pebble reaches some maximum height and it comes back down. Let me just adjust the diagram a little bit to make it look a little bit. Anyways, leave it. So let's say that represents the path of the pebble, right? So what information that we have? We have initial velocity, of course, considering the vertical direction first. Now the pebble lands at some distance from the foot of from the cliff. Let's call that distance x. And it would have fallen a vertical distance y. Right? So, what information do we have? We're talking about it being projected upwards. So using the sign convention, up is positive. So therefore we know that A is equal to minus G, that is equal to minus 10 meters per second squared. And of course, we're talking about the vertical direction. So vertically, right, we have that piece of information. The initial velocity U So u would be equal to 10 sine 30 degrees, and sine of 30 is equal to a half, so this is equal to 5 meters per second, meters per second. So the initial vertical velocity is 5 meters per second. And of course, you're given a time of 6 seconds. So t equals 6.0 seconds. And we're asked to find the height of the cliff. So therefore, this means that we want an equation that is going to involve displacement s. And so those equations don't apply because this motion is not representative of the type of motion for which we'd have derived those equations, right? So we basically have to apply the equations of motion in a vertical direction modified somewhat. Equations modified somewhat. So we want to find the vertical displacement s. So if you recall our equations of motion, if we have u, we have a, and we have t, and we want to find s, we're going to use s is equal to ut plus a half at squared. Now bear in mind that when we're applying these equations, especially to vertical motion, we have to remember our sign convention. And in this particular case, we're using the sign convention that up is positive. Now what exactly does this mean? So we say up is positive. When you're using that sign convention, it means our acceleration a is equal to minus g. While the body is moving upwards, it will have a positive velocity. While moving down, negative velocity. While the body is above some reference point, the displacement will be positive, and when it is below, the displacement will be negative. So if we calculate the displacement and it is negative, then that should give us an idea of the position of the body relative to its reference point. So we say s equals ut plus a half at squared. So we have s is equal to 5 times 6 plus a half of minus 10 times 6 squared. 5 6s, that is 30. Half of minus 10, that is minus 5. 6 squared, that is 36. 5 times 36, that is, well, minus 180. And so we get minus 150 meters for the net displacement after 2 seconds. So the net vertical displacement is minus 150 meters. So what this basically means is that the object lands at a vertical displacement of 150 meters below its initial reference point or its initial level of projection, and that is why the displacement is negative. And therefore this tells us that the top of the cliff is, or we could say the sea is 150 meters below the cliff, and therefore the cliff is 150 meters high, right? So therefore the height of the cliff h is equal to 150 meters. Good? Now for part B, they want us to find the distance from the base of the cliff at which a pebble falls into the sea. So for part B, so since we want to find the horizontal distance, we have to consider the horizontal direction. So horizontally. Now if we look back at the initial situation, remember that whenever our body is projected at some angle, to say the horizontal, it will have a vertical component of velocity and a horizontal component of velocity as well. So in this case, this horizontal component will be 10 cos 30, and of course, you know, the initial vertical component will be 10 sine 30. Now horizontally, we know that the resultant force is 0, and we ignore the effects of wind resistance, and therefore the velocity is constant. So we can say that horizontally, the velocity Vx equals V cos theta, which in this case is equal to 10 cos 30, and this is approximately equal to 8.6 or 8.7 meters per second, right? So throughout this object's flight, its horizontal velocity will be 8.7 meters per second, right? And since of course we know that speed is equal to speed is constant, then if speed v equals distance over time, then this therefore means that distance is equal to speed times time. And so the horizontal distance traveled, or the distance that it lands from the foot of the cliff, would be equal to x is equal to 8.7 times 6 seconds, and that gives us 6 8 is 48, 6 7 is 35, so 51.5, right? So approximately 51.5 meters. right, which you could round to 52, but let's just take that as 51.5 meters. So therefore, the pebble lands a distance of 51.5 meters from the base of the cliff or from the foot of the cliff. All right, so we'll next look at question 7 from our worksheet on projectile motion. So question 7 says a particle is projected from a point which is 2 meters above ground with a velocity of 40 meters per second at an angle of 45 degrees to the horizontal. Find its horizontal distance from the point of projection when it hits the ground. Right? So basically, let's, as we usually do, we basically use a diagram to represent this situation, right? So this object, the particle, projected from a point which is 2 meters above the ground. So let this be the point which is 2 meters above the ground. So let this be the ground level. Right? So it is projected at an angle of 45 degrees. So and it's going to strike the ground, right? So the angle the path makes to the horizontal, that is 45 degrees. And its initial velocity of projection, that of course is 40 meters per second. Right? Now the point from projection is 2 meters above the ground, right? And they want us to find the horizontal distance from the point of projection when it hits the ground, right? Now, the way we'll approach this question is, what we will do is we'll find the time taken to actually hit the ground, and we know that in that time its velocity would have been constant, and therefore we can use that information now to find the horizontal distance traveled. So they want us to find the horizontal distance, and let's call this horizontal distance x. So let's look at the vertical direction first. So vertically, we know that A is equal to minus g equals minus 10 meters per second squared. The body's velocity will have a vertical component, and of course it will have a horizontal component as well. So the vertical component, and it will have a horizontal component. So the vertical component would be 40 sine 45, and the horizontal component will be 40 cos 45. Now these two will actually be equal because 45 degrees is its own complement. So sine 45, that's proper, yeah. So remember that complementary angles had to give 90 degrees. So 45 is its own complement, and so sine 45 is equal to cos 45. So vertically, we know A is equal to minus g equals minus 10. The initial vertical velocity u is equal to 40 sine 45, right? And we can work that out. So that gives us 28.3 meters per second. Right? Now, when it strikes the ground, it will be 2 meters below the initial level of projection. Right? So when it strikes the ground, it will be 2 meters below its initial level of projection, and therefore its net vertical displacement S is equal to minus 2 meters. Right? So when the object is projected, as it rises, its vertical displacement increases, and while it is above the reference point or the initial level of projection, the displacement is taken as being positive. Right? It returns to the initial level of projection, say there, and therefore that means at that point the net vertical displacement is equal to 0. But it doesn't stop there. It continues and strikes the ground 2 meters below the initial level of projection, and therefore when it hits the ground, the net vertical displacement is equal to 0. And of course, we want to find t. T. So, t. So, with the user equation, S equals ut plus a half at squared. And so we have minus 2 is equal to 28.3 t. Half of minus 10 is minus 5 t squared. Right? And if we bring all the terms to one side, we get that 5t squared minus 28.3t minus 2 is equal to 0. Right? Now this basically is our quadratic, is a quadratic in t. Right? So this is a quadratic in t, and so basically we have A equals 5, B equals minus 28.3, and C is equal to minus 2. And we should be able to solve for this using the quadratic formula, which in this case is going to be given by t is equal to minus b plus or minus the root of b squared minus 4ac all over 2a. Right? So we will solve this equation to find the time t. So we will solve this equation for t. So we have our quadratic formula. A is equal to 5, b is equal to minus 28.3, c is equal to minus 2. So therefore we have t is equal to minus, so this would be minus 28.3, which is 28.3, plus or minus the square root of minus 28.3 squared minus 4 times 5 times minus 2. And all of this will be over 2 times a, which is 5. So when you work out all of that now, we basically get t is equal to 28.3 plus or minus the square root of (841), and this is all over 10. And so we get t is equal to 28.3 plus or minus the square root of approximately 29. Right? Approximately 29. Yeah. Function root 841. Right, so approximately 29, and this is all over 10. Now we're calculating time, and we know that time cannot be negative, so time must be positive, and therefore we will disregard the minus sign here. So basically what we're going to get is 29 plus 28.3, which is 57.3 divided by 10, and so this gives us 5.73 seconds. Good? So that's just the first part. Now we need to go ahead and find the horizontal distance traveled. Right? Now we know that basically horizontally the velocity will be constant, and so therefore speed is equal to distance traveled over time taken, and therefore it means that distance is equal to speed by time. So the horizontal distance x would be equal to the horizontal component of the velocity 40 cos 45, which, as I mentioned before, 40 cos 45, same thing as 40 sine 45. So therefore this would be equal to 28.3 times the time, which is 5.73 seconds, and this therefore gives us approximately 162. So we're looking at a second approach to question 7. Now looking at the question, realize that basically we weren't required to calculate the time. So because calculating the time was not a requirement, we could actually have approached a question differently. Now what we have is basically we have the vertical displacement y equals minus 2, because when the object strikes the ground, it is 2 meters below the initial level of projection, and so the vertical displacement y is equal to minus 2. We have the angular projection theta equals 45 degrees. We have the velocity of projection 40 degrees, and we want to find x. So if we look at our list of equations pertaining to projectile motion, we see that the equation for the path, we can actually use that and we can to calculate x. So using that equation, we have y equals x tan theta minus g x squared 1 plus tan squared theta all over 2v squared, right? So substituting the values now that we have, we know y is equal to minus 2. So we have minus 2, that is equal to x. Now theta is equal to 45 degrees, and tan of 45 degrees is equal to 1. So we'll just put the value. So x times 1 is just x. And coming over here, we have minus g, which is 10 x squared times, again, tan of 45, that is 1. 1 squared is 1. So 1 plus 1 is 2. This is minus 10x squared times 2. And this is all over 2v squared. What is missing? Right, 2v squared, where of course v is 40. This is 2 times 40 squared. Right? So right away we can see that basically, well, these 2's will cancel. And so we have minus 2 is equal to x minus 10x squared over 1600. Right? So that is what our equation looks like. We could simplify that a little bit further though before we actually do any cross. So we could say 10 into itself goes 1, 10 into 1600 goes 160, and so we have minus 2 is equal to x minus x squared over 160. Now because we want to solve for x, we want to get rid of this 160 and bring all the terms to one side. So we'll then multiply both sides of the equation by 160, and that should give us minus 320 is equal to 160x minus x squared. And if we bring all the terms to the left hand side, we basically get x squared minus 160x minus 320 is equal to 0. Right, so once again we end up with a quadratic which we'll have to solve, and we'll solve this quadratic of course by using the quadratic formula. So we see that a is equal to 1, b is equal to minus 160, and c is equal to minus 320, and so we have x is equal to minus b plus or minus root b squared minus 4ac all over 2a, and so we have x equals, so that's 160 plus or minus square root of minus 160 squared minus 4 times 1 times minus 320. And this basically, this is all over 2. Right? So this gives us x equals 160 plus or minus. Now this works out to give us 26,880 all over 2. Now, because we're calculating distance, and the distance will only be positive, we will basically ignore the minus sign, and so the one value that we'll be getting will be the horizontal distance which the particle landed from the initial level of projection, right? So this gives us x is equal to 160 plus, so root 26,880 gosh, man. That gives us 163.9 or 164, so approximately 164 over 2, and this therefore gives us x is equal to 162 meters, which of course is very close to the previous answer we got when we actually applied the previous approach. So previously what we did was to consider the vertical direction. We found the time taken to strike the ground, and then because the horizontal velocity was constant, we used that time to calculate the the horizontal distance traveled, and we got something very close to 162 meters. All right, so let's look at another question from our worksheet. This one says, so let's look at number 9. A gun is fired to hit a target level with it, but 1,000 meters away. If the muzzle velocity of the gun is 200 meters per second, and the shell it fires has to pass over a tree 15 meters high and 50 meters from the gun, find the angular projection necessary. So once again, we'll try to represent the situation using a diagram, right? So the gun is to hit a target which is 1,000 meters away from it, level with it. So what this is basically telling us is that the horizontal range of the projectile is going to be equal to horizontal range of the projectile is equal to 1,000 meters. So let this be the path. Right? Now, as mentioned, there is a tree. So this distance, let this point be O and this point be A. So the horizontal range is equal to 1,000 meters. So OA is equal to 1,000 meters. But somewhere between O and A, there is a tree of height 15 meters, which we're told is 50 meters from the point of projection, right? So the gun is here at O, and there's a tree. Try my best to draw a tree, right? So there we have the tree, and the distance of where the gun is to be launched from where the tree is 50 meters, and of course the tree is 15 meters tall. So we want to find the angular projection necessary for the target to be hit. Now, for the target to be hit, it simply means that the trajectory must be over the tree. If it falls below that, then it means that the bullet will strike the tree and it will not be hit. So we know that essentially what we have, information that we have the velocity. Right, it's 200 meters per second at an angle. Oh, we don't know the angle. So the velocity is 200 meters per second. Right, so the launch velocity V is equal to 200 meters per second, and the horizontal range R is equal to 1,000 meters. Right, so what we will do is we will use our range, and we will find the possible angles of projection. So we're going to say that R is equal to V squared sine 2 theta over G. So this means that sine 2 theta is equal to RG over V squared, right? So we have sine 2 theta is equal to R, which is 1,000, times G, which is 10, divided by V squared, which is 200 squared. Right? So we have sine 2 theta is equal to 10,000 divided by 40,000. So we have sine 2 theta is equal to 0.25. And so we say 2 theta is equal to the sine inverse of 0.25. And we go to our calculator. So sine inverse of 0.25 is 14.5 degrees. So we have 2 theta is equal to 14.5 degrees. However, we know that sine is also positive in the second quadrant. So the other possible value for twice the angle theta, we take away 14.5 from 180, then that basically gives us 1 175.5. So two values of 2 theta are 14.5 degrees and 175.5 degrees, and therefore this would mean that theta possible values are 7.2 or 7.3 degrees, or half of 175.5, that's about 87.8 degrees, 87.8 something. So 80, let me check, let me make sure my math is not off. So 175, so minus 180 divide, or 165.5 rather, 165.5, right. So 165.5 we divide it by 2, that should give 82 point something, right? So 82.8, so or 82.8 degrees. So these are the two possible angles of launch to strike the target. Now, how do we know which of them is the preferred angle, or is the angle which will actually escape the tree? Now let's examine what is happening here with the tree. So the tree is 15 meters tall, and it is 50 meters away from the point of projection. So what we can do is basically we can calculate the angle formed by the diagonal, and if that angle happens to be, say, less than 7.3, then we know, or greater rather, if the angle appears to be greater than 7.3, we'll know that basically with this launch angle, it will strike the tree. So let's examine that little section there. So once again, the tree is 15 meters tall, and at 50 meters from the point of projection. So what we have here is a right angle triangle, and let's call this angle theta. This is 15, this is 50. And so we can say that tan theta is equal to 15 over 50, which is the same thing as 3 over 10, which is 0.3, and therefore theta is equal to tan inverse of 0.3. And what does that give us? So the tan inverse of 0.3, that gives us 16.7 degrees. So theta is equal to 16.7 degrees. So this alone is enough to suggest that if the object is launched at an angle of 7.3 degrees, it simply will not surpass the tree, and therefore the angular projection necessary would be 82.8 degrees, right? So if it was to be launched at an angle of 7.3 degrees, then it would not surpass, it would not pass the 3, it would not travel over the 3, but would actually strike the 3, and therefore the angular projection necessary is 82.8 degrees. All right. Let's look at one more question. So, question 13. Question 13 says, a particle is projected from a point O with initial speed of 50 meters per second. The particle just clears a wall which is 50 meters high and 100 meters horizontally from O. Find the two possible angles of projection of the particle. So once again, we represent our situation using a simple diagram, right? So the particle is projected from O, point O, with a speed of 50 meters per second. And the particle just clears a wall which is 50 meters high and 100 meters horizontally from O. So let's try to represent the possible path of the particle. So once again, let that be the path of the particle, right? And let this be O. So the particle is projected with a velocity of 50 meters per second. Right? Now what we're told is that the particle, it just clears a wall of height 50 meters, which is 100 meters from O. So let's say that is a path of the particle, then it just clears the wall. Right? So when you say it just clears the wall, that has certain implications. Right? So that is a wall right there. And the horizontal distance of the wall from O is 100 meters. And the height of the wall is 50 meters. So when we're told that the particle just clears the wall, it basically means that at this point of the particle's trajectory, the horizontal distance traveled would have been, when x is equal to 100 meters, y is equal to 50 meters, right? So when x equals 100 meters, y is equal to 50 meters approximately, right? Because it just clears the wall. So, and of course, you know that the velocity of projection, v, is equal to 50 meters per second. So this is another situation where we have x, we have y, we have the launch velocity v, and we want to find the two possible angles of projection. So that clearly suggests that we're going to have to use the equation of the path. So what we'll simply do is substitute our values into the equation of the path. What we'll then get is a quadratic in tan theta, which of course you will solve to find the two possible values of theta. So let's just substitute. So we have y equals x tan theta minus gx squared 1 plus tan squared theta all over 2v squared, right? So if we were to just substitute the values here, we get y, which would be 50. So 50 is equal to 100 tan theta minus g, which of course is 10, x, which of course is 100, so that's 100 squared, times 1 plus tan squared theta, and this is over 2 times 50 squared. Right? So we'll go and simplify as far as possible. So we get 50 is equal to 100 tan theta minus 100 squared, that is 10,000. 10,000 times 10, that is 100,000. So this is minus 100,000 times 1 plus tan squared theta. And this is all over. Now 50 squared, that is 2,500. And 2,500 by 2, that is over 5,000. Right? So if we divide through, 3 zeros cancel, then we get 5 into 100, that goes 20. Right? So what we therefore have is 50 is equal to 100 tan theta. And then this would be minus 20 times 1 plus tan squared theta. So we can now basically expand our brackets and simplify. Or we can actually simplify a little bit first before we actually proceed to expanding the brackets. Now each of these coefficients or numbers, 50, 120, are divisible by 10. So dividing through by 10, we get that 5 is equal to 10 tan theta minus 2, 1 plus tan squared theta. And we expand the brackets now, we get that 5 is equal to 10 tan theta minus 2 tan squared theta. We bring all the terms on the right to the left, they're going to change sign, and so we get 2 tan squared theta minus tan theta plus 2 plus 5 is equal to 0. And our equation becomes 2 tan squared theta minus tan theta plus 7 is equal to 0. Right? And this essentially is a quadratic in tan theta. So for instance, we can say let tan theta is equal to some variable. Let's call it p. And so therefore this becomes 2p squared minus p plus 7 is equal to 0. So we'll then solve for p and then equate to tan theta and find the possible values of angle theta. Right, so this is basically our equation which you'll have to solve. Oh, right, I recognize I made a little mistake here. So in bringing over the terms, I somehow forgot to put the tan to the theta. So this should be minus 10 tan theta. So minus 10 tan theta. This again is minus 10 tan theta. So if we let tan theta equals p, then the equation becomes 2p squared minus 10p plus 7 equals 0. And that is our equation that we'll have to solve. When we solve that equation, we'll then let tan theta equals p, and then we'll find our two possible values of our angle theta. Alright, so the mistake has been corrected, and so this basically is a quadratic that you'll have to solve to find p, and then when you get the values of p, you say tan theta is equal to that, and you find the values of p. Now bear in mind that when you're solving for the angle theta, we're talking about angular projection, and typically those are two acute angles. So the values of theta are supposed to be two acute angles. So we have our equation, and we then solve for p, and then of course we'll find our possible values for the angle theta. So let's make some space, and let's leave that. So we have our equation 2p squared minus 10p plus 7 is equal to 0, which of course is another quadratic equation which we'll have to solve by using the quadratic formula. And so we have a equals 2, b equals minus 10, and c is equal to 7. And so we say that p is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. And so we get that p equals, so minus 10, that is 10, plus or minus square root of minus 10 squared, that gives us 100, minus 4 times a, which is 2, times c, which is 7, and this is all over 2a, and the value of a is equal to 2, so this is all over 4. So 4 2 is 8, 8 7s are 56, and 100 minus 56, that gives us 44. So p is equal to 10 plus or minus root of 44 all over 4. So this gives us 10 plus or minus root of 44 . So that's 6.6. So let's call that 6.63. This is all over 4. And so therefore what we have is p is equal to 10. So taking the sign at the top, the 10 plus, so this is 16.63 divided by 4, or 10 minus 6.63, that's 3.37. P is equal to 3.37 divided by 4. So this gives us p is equal to approximately 4.16, or p is equal to 3.37 divided by 4, approximately 0.843. So having found the values of p, now we must remember that p is equal to tan theta. So we say, of course, but p equals tan theta. So we have tan theta equals 4.16. So theta is equal to tan inverse of 4.16, and that gives us 76.5 degrees. And the other value of theta is obtained by using that there. So we say now or tan theta is equal to 0.843, and therefore theta is equal to the tan inverse of 0.843, and this gives us that theta is equal to 40.1 degrees. So therefore, these are our two possible angles of projection, 40.1 degrees and 76.5 degrees. And this was question 13 from our worksheet on projectile motion.